Good morning. My name's Kevin Farley. I'm here with my colleagues Elaine Dormel and Xiaochen Wu. We're all program managers in the SQL team working on the Hyperscale project. It's fun to be able to talk about it publicly. So how many of you guys are working on something that doesn't deal at all with data? Okay, so that's why we're here. How many of you have challenges with data that gets really big? That's also why we're here. So we're talking about Hyperscale as a way to have a data platform that can grow so you don't have to worry about how big it gets. Hello? There we go. So just set context, this is just another Azure SQL database. So it inherits all the goodness of the Azure platform. We have Azure SQL Database, SQL Server on Azure virtual machines, Azure Database for MySQL, Postgres, MariaDB, and all of them live within the Azure framework, the Azure infrastructure. And so that infrastructure gives us a lot of benefits. Intelligence, so we have the ability to monitor the execution of customers' databases without looking into, we don't get to see what's in the database, but we can see how it's performing. And we can make adjustments to tune for it in the background. We have intelligent security, which looks at connections coming into the database and looks for patterns that would indicate somebody's trying to break into your database. We can block them, send you alerts, let you know about it. So there's a lot of benefits to just being on the Azure platform. It's flexible. Hyperscale is a prime example of flexibility. You've got all kinds of dimensions of flexibility here. It fluidly scales in cores. It fluidly scales out in terms of size, and as well as replicas for scaling out read performance. Elastic scaling, so you can scale up and down as you need without it being a big disruptive event. There's resource governance available as well. Trusted, this is one of the most trusted platforms on the planet. We have every certification, security certification that is possible to get. If they invent a new one, we'll get that one too. Always encrypted is available now with secure enclaves, which means that you can do a lot more with the always encrypted technology still in a very secure way. So the engine can get access to the data to do things like sorts, but without the engine actually seeing the data. It's in a secured, walled-off part of the hardware. Business continuity, HA and DR is part of the Azure platform, and you get to scale that however you want. You can have just a single database with no replicas and no DR for your prototyping. You can have hot standbys. You can have replicas in other regions. So however you want to scale that, that's up to you. Enterprise security isolation, again, nobody else gets to see your data. It's truly secure and isolated. So I'm going to give a brief overview of Hyperscale, and then my colleagues will come up and talk about the architecture and also how it applies specifically in a development world with CI/CD pipelines and how we can contribute to that. So Hyperscale is a concept within Azure Azure Databases all up for big scale. So there's the concept of having fluid scale to be able to scale up and down at need. It applies both to Azure SQL Database, which is what I'm here to talk about, but as well as the Citus Hyperscale version, which applies to the open source databases. I believe they had a session yesterday. We have back-to-back booths in the expo hall. It's purpose-built. It's built for the cloud, scales compute, storage, memory, or all three, optimized for different scenarios, and it's customized by database engine. So the Citus is optimized for the open source database engines. Hyperscale for Azure SQL Database is obviously optimized for the SQL engine. So the implementation is going to be different, but the overall theme, the driving theme, is scalability, fluid scalability, takes the worry out of database scaling. So if you've been on business critical Azure SQL Database and you're up against the 4 terabyte limit, where do you go? Down to general purpose? That probably won't meet your performance needs. So this removes that barrier. So what are the challenges with running very large databases? And by very large, I'm talking about in the 100 terabyte range. Anybody think about what those challenges might be? Piece of cake? So anything to do with size of data gets really painful. So backups or stores can take days if you're in that class of database. Ongoing performance can degrade performance. So if you're doing a streaming backup of a 50 terabyte database and it takes 4 days to complete, during that 4 days, your I/O system is going to be hammered. So it impacts, it's not just that that operation takes a long time, it's just not just that if things hiccup during that time, you're having problems, but it's going to degrade your performance in your mainline database. It can cause outages and downtime. And then what happens if you need to change the specs of the hardware? If you're going to move to a new box, that's really painful. You're going to copy that much data or physically move the disks if it's on site. That can be a serious impediment. So all of those things are related to the size of data you're working with, and they get more painful the more data that you have. Scaling compute, so the logistics of moving to a larger box. Economics of scaling for peaks. So if you're dealing with that class of database, that's a pretty substantial piece of hardware. And if you have to provision that for as big a maximum peak as you might hit in your workload, you're going to pay for that all the time. You get that peak to use it occasionally. So that's a financial challenge. So these are all the problems that we looked at out in the database world when we set about looking at hyperscale. These are the problems that we aim to fix with this feature. So what is Azure SQL Database Hyperscale? So it's storage. It's a new storage architecture for SQL. We took the SQL engine as it existed and split the query engine from the storage engine. So those have always been distinct layers of code within that one process. We physically split them. So the storage engine is now in a series of VMs as a scale-out microservice, if you will. Each VM manages a range of data pages. So we can just keep adding more as we need. So we can grow very fluidly that way. Cloud native, it's architected for the cloud. A lot of people ask me, well, when is Hyperscale coming to SQL Server? As you'll see when we get through the architecture, there's a lot of what makes Hyperscale work that depends on the infrastructure we have within Azure, the ability to provision VMs and reconfigure things on the fly, that we don't know how to manipulate that in your environment. So someday that may happen. Likely it'll be in the context of a Kubernetes sort of orchestrator, but that's a ways down the road. This work has been architected for the cloud. Seamless compatibility. So I mentioned that we split off the query engine from the storage engine. The query engine is unchanged, and it is the same code as Azure SQL Database and SQL Server. The query engine is absolutely the same code. So you have complete compatibility as far as the performance, as far as the behavior of all those queries. You don't have to adjust when you're moving to a hyperscale database. You don't have to rewrite. It's just compatible. Performance, VLDB operations without the VLDB headaches. We're making some bold claims there, and we'll show you how that works. And no limits, scale, compute, and storage. So compute scales up, I think right now we scale up to 80 cores per compute node, and you can add up to 16 compute nodes with one writable one and the rest being read replicas. Storage, we're claiming support for up to 100 terabytes with this database. There's nothing architecturally significant about 100. It's just a round number. So we can go beyond that. It just takes a long time to accumulate that much test data. Large database support for 100 terabyte plus. So what does it bring to the table? SQL database compatibility. So there's no new syntax, no changes in queries. It's just another database. You can manipulate it with the portal as you would Azure SQL databases. You can manipulate it with PowerShell. You can manipulate it with T-SQL. Lots of different ways. They all work. It's just another SLO as far as Engine's concerned. Tools for management APIs, Azure Management Portal with HTML5 support, SQL Server Management Studio, Data Studio, all those work the same on an Azure SQL Database Hyperscale as any other Azure SQL database. So, in other words, the tooling is no different. You don't have a special Hyperscale variant of tooling you have to figure out how to use. It's the same tools you've always used, just use them on a bigger database. Flexibility, seamless support, development online, offline, and across premises cloud-designed apps with Visual Studio. So extend existing applications into the cloud with the DAC framework. So there's a lot of flexibility there that's just inherited as part of the goodness of the SQL Azure platform. Reliable and available. So you have multiple levels of redundancy. We'll get into that in the architecture, but for every component within Hyperscale, there's hot standbys and secondaries to make sure that if a component ever were to fail, there's somebody to pick it up immediately. Lots of levels of redundancy there to make sure that your data is safe and that your operations are not interrupted. 99.99% availability depending on the number of replicas that you configure. Obviously, if you have one replica running it and we have to restart that, that's going to take longer than just failing over to a hot standby. And that eats into the number of minutes per month you get to get 4 nines. So we're kind of introducing the concept there that you can scale your availability by the way you configure the database. Scaling quickly. So if you need to increase your core count in business critical, that means in the background we're copying all of your data to a new VM that has more cores in it. That doesn't happen here because we've separated compute and storage. So we can scale the compute without moving any data. It's much, much faster and more fluid. Data and cores scale independently. You can scale a 50 terabyte database in minutes. So with that said, let me show you how this looks. So I have an Azure SQL Database server here. I can create a new database. My demo from blank database, pricing tier. So the only thing that's different about creating a Hyperscale database is you choose the Hyperscale performance tier. Where there's been business critical and general purpose or premium standard before, now we've added another performance tier, which is Hyperscale. There's 2 generations of hardware. Gen 4 is the older hardware. Gen 5 is the new stuff. We won't be expanding the footprint of Gen 4 hardware because we can't get it anymore. So Gen 5 is the new. Gen 5 goes up to 80 cores, so you can scale that anywhere from 2 to 80 cores. I'll create a small database to keep my manager happy. Choose the number of secondary replicas. So the default is 1 secondary replica. So you have your primary and 1 standby secondary, which serves both HA duties as well as it's available as a readable secondary. Okay, so the other checkbox you need to acknowledge here, and full transparency, at this time, once you put the data in Hyperscale, you can't get it back out other than export import. That will come in the future. You can actually, with just a scaling operation, transition a traditional Azure SQL database into Hyperscale. Right now, that's a one-way path, and we make you explicitly acknowledge it. We don't want anybody to get surprised by that. Okay, so I apply it. Okay? That's what it takes. That's creating a hyperscale database. No different than any other SQL database. And the parallels are exactly the same if you're using PowerShell, Azure Shell, all of those methods. It's just a different SLO. High performance, low latency high throughput for large databases. Backups are snapshot-based. So we'll, again, get into the architecture of that, but the application never feels the backups because it's snapshot in the storage layer, and that is buffered by cache. So the application's never going to feel that, and that allows us to do a very rapid database restore. So I'm going to do a quick demo also of migrating an existing database to Hyperscale. Actually, I did not, did I? Okay, this is going to take a little longer than I planned. So I'm creating a standard database, S0, and we're going to scale that. Okay, migration is the database I chose. To move this into a hyperscale database, you just choose configure. Right now that's in standard. Move over to the hyperscale tier. Gen 4, 1 core. Yes, it's a one-way trip. Apply. That's it. That's what it takes to convert a traditional database into hyperscale. Any questions on that? Okay. With that, I'll hand it over to Elaine.
Working. Yeah, there we go. Okay, awesome. So I'll be covering the underlying architecture. So just as a show of hands, who here has a reasonable grasp of how SQL works today? And more specifically, how SQL would work in Azure today. Right, so there's a couple of people. So I'll sort of try to keep it at a reasonable level. So essentially what we've got is there's a couple of new concepts that we've introduced with Hyperscale that you won't necessarily see anywhere else. And that's all around how we have architected specifically for the cloud. So some of the big issues we've always faced with SQL is our interaction with storage layer. So, I mean, moving data around, moving data from like persistent storage up into your buffer pool, those things take time, and they've always taken time. So instead of, if you look 5 years back, traditionally, if a SQL database was slow, people threw resources at it, and they kind of hoped that it would go faster. But that's not a feasible model anymore, so we've architected away from that. And we've introduced the concept of having a completely separated compute layer. We've introduced a standalone log service, so your logs are no longer dealt with directly by the compute node. We've got page servers. We'll dive into all of this a bit more. And then there's the remote storage layer where the actual data files go and live. So I'm going to walk through this one of these at a time, and then I'll show you the whole architecture, because if I show you the full architecture up front, most people would leave. So we'll start like piecemeal, and we'll work through where we are with these deployments. So very similar to what you would get today, you have a primary compute node, and that primary compute node, just like everything else, has compute, it has memory, and it has storage. In this specific example, the storage that is here is directly attached SSDs, right? So these are SSDs that run through the PCI ports, so it's highly performant, it's very fast, it's some of the fastest storage you're gonna get, right? Now, a compute node is configurable anything from 1 core to 80 cores, depending on the generation of hardware that you're sitting on. And what we do here that's very different from what we do in our other deployments is instead of storing your data files directly on the SSDs in the compute node, we've actually used the technology that we introduced in SQL 2016, which is RBPX. It stands for Resilient Buffer Pool Extension. So it allows you to expand your buffer pool onto solid states that you have in your environment, right? So your actual data files, so the MDFs and the LDFs that you're used to in the SQL world don't actually live in the primary compute node. And that's what will allow you to do the scale-up operations without having to move data in and out of the system. So the whole SSD layer here is essentially part of your caching layer. Then very similar in the secondaries that we have available, it's exactly the same concept that you would have there. You have a node that has compute and CPU, it has cores and it has memory and it has these same directly attached SSD drives. The big difference being here is SQL is not a multi-master environment, so you can't have multiple reads from multiple nodes. So all of your secondaries are read-only. So you can only issue workloads that'll sort of fetch pages, not write pages necessarily. But all of your secondaries can also be hot failover targets. So if you have a failure in the primary, we would just fail over to one of the secondaries and it would change to read-write. And that's all metadata operations, right? So failures are dealt with very quickly. From a developer perspective, what we always tell people is all you really have to do is build retry logic into your apps, right? So if you have some type of retry logic for when you try to contact the database, that metadata, if there's a failure, the metadata operation will kick in and you will immediately retry against the new node that has come up in place of your primary. The one thing that's very important about the secondaries as well as the primary nodes that we mentioned is that RBPX layer that we have that runs across your SSDs is non-covering, right? So it does not contain all of your data. It only contains portions of your data. And the way that SQL determines what data sits in that buffer layer is essentially the same way it does it today, right? So data that you access more and more has a very high likelihood of landing up in this localized caching zone on the primary and secondaries. Now we'll look at the specific page servers. So a page server is essentially, it is a very similar concept to what we just looked at. You have cores attached, you have memory attached in the page server, and it actually runs a SQL Server thread on it, right? So it is a, for lack of better words, it is a SQL Server engine. But what we do is each page server gets allocated as 128 gigabytes, and these actually get deployed onto Azure Remote Premium Storage, which is also an SSD layer, right? So you have two layers of SSD. You have the super performant SSDs that are locally attached, and you have the other one that's remote. So for people who are familiar with SQL, think of a SAN, for example, where you have a network-attached device that you have to go access, and there is latency that now lives because you're doing it over a network. So obviously, even though these are SSDs, your data latency into the page servers is slower than what it would be for the local SSDs. But essentially what we do is we create 128 gigabyte allocations at a time. All of this storage is redundant, so there's multiple copies of the storage so that if we suffer failures, we can fail over to another one. So all of that is covered for you, and you don't have to worry about any of that. A lot of what I'm talking about now, and when I show you the big architecture, might seem very complex, but from a customer perspective, all of these things are transparent. You don't have to worry about the creation of these things, the placement of these things. They sort of, it all happens in the back end, but you get all the benefits for us doing this, right? So one of the key things that is important here is similar to what we saw in the primary and the secondary nodes where you have the RBPX layer. Because this is SSDs, we have also got an RBPX layer that runs on the page servers. The big difference here is that this is a covering RBPX. So all of your data physically lives in this RBPX layer. It's still not the data file. If you look down towards the bottom, we then have a Azure standard storage account for each page server. And in that standard storage account, we then go place the MDFs and the LDFs. Right? So theoretically speaking, you should never be accessing standard storage because standard storage is super slow. It lives far. There's high latency. You don't want to be accessing that layer. But because the RBPX on the page servers is full covering, all of your data will live up there. And then the really hot data, so things you use very often, will actually go live on the compute node themselves. The other thing that's important here is because your actual data files are living on standard storage, we have moved away from doing sort of a traditional sort of backup schedule where you do fulls, diffs, and log backups, and we now do file snapshots on the MDFs and LDFs that live on the remote storage. And that's how we can ensure that backups have zero impact on your compute node because they're isolated from each other, but also this allows us to do things like Kevin was mentioning where we can do constant time operations. So we can restore a database irrespective of whether it's 1 terabyte or 100 terabytes in the same amount of time. Right? Because we have these small allocations, we have the snapshots, and it is really just a metadata operation around moving those snapshots where they should belong. The next concept that we need to look at is the log server. So also kind of different from what you're going to get in SQL today. The log service kind of has two parts to it as well. It has what is the log landing zone today. So when you write a transaction, you essentially write into that landing zone. There is a service that runs in the log service that can pick that up and hosts it in its buffer cache, and then it will apply it wherever it has to. Very similar to what we saw in the page servers, there is also a remote storage allocation for every log service that is available. In that remote storage location, that's where your LDFs and all of those things will go live. But the big difference here being is from business critical, general purpose, or even on-prem SQLs, we actually never clear your log out because we destage the log once it's been committed everywhere down into a long-term log storage, and we never clear that layer out. That's so that we can do things like point-in-time recovery, so you can recover a database to a specific point in time down to a second for the last 35 days, and that's because we hold on to your log, we have all the snapshots, so we can kind of align things, we can look at the LSNs, and we can restore the databases to very specific points in time. Here is the full architecture, right? So you have your compute layer at the top, which consists of a single primary and up to 4 readable secondaries today, right? And that layer, because it is completely isolated from your storage, you can scale that up and down, you can add more secondaries, and it's a very constant operation. So it's a very predictable thing. So you know how long it's going to take you to go from 2 cores to 80 cores, and there's no sort of guessing game. Whereas in the deployments we have today, sometimes what happens is you'll go, okay, when I go from 2 to 80 cores, but then you've got to get moved into an environment where there are 80 cores available, and that movement of data is what takes a ton of time, right? It takes a lot of time to move data like that. You have the page server layer, which has its covering RBPX, and you'll see there's you have these 128 gigabyte allocations, and from an architectural standpoint and a technical standpoint, even though we say the upper limit is 100 terabytes, theoretically there is no upper limit, right? You can continue adding these things indefinitely. Sure, there'll come a time when either we'll run out of storage or you will run out of data to store there. And then respectively to that, you have all of the remote storage accounts where the actual data files go and live. So how this all gets presented up to SQL for the end user is for every data file that you have, or for every page server that you have, it essentially just appears as another file inside a database. Right? That's how SQL perceives it. And as an end user, this is not the easiest concept ever, but as an end user, you only really have to worry about the SQL surface area. You don't worry about anything past that. Right? We're just showing you the architecture so you understand how we do a lot of the things that we do and how we get the performance that we sort of claim that we can get. Okay, so let's look at a very specific scenario here. So for a write operation, I want to write data into my database. Essentially, the user or the application will issue a transaction to the primary node, right? The primary node will then go and write that down into the log landing zone. Now, very different from business critical or general purpose or even on-prem SQL environments. The minute the transaction has been hardened in the log landing zone, we consider transaction commit. Irrespective of how many secondaries there are, irrespective of how many page servers there are, the minute the landing zone has hardened that log, it's considered transaction commit. So because of this, we can actually get much higher throughput of data, right? So like if you're doing bulk write operations and things, your throughput into that log is considerably higher than any of the other deployments that we have today in this environment. And today, that log landing zone runs on top of remote or premium remote storage, which is an SSD layer. One of our sort of future innovations is to move that onto ultra SSDs, where the latency into that log area will be sub-millisecond, right? Today it's about less than 2 milliseconds, so it'll go sub-milliseconds in kind of the future iterations. The minute that log is hardened, what happens is the log service will pick it up, it'll stage it inside its buffer cache, and it is then responsible for simultaneously and asynchronously applying that log, my diagram broke, to both the secondaries and the page servers, right? So if you think about an always-on configuration today, a lot of your overhead when writing large transactions is waiting for all of the secondaries to acknowledge a write operation. So here we've moved it from being a synchronous to an asynchronous operation. And from a high availability standpoint, if that log landing zone has zone redundant and local redundant copies of itself, right? So even if the actual service thread had to go down, your database would still be fully available. All that would happen is the secondaries and the page servers would fall a bit behind. When the log service came back up, it would just continue seeding records down into the secondaries and the page servers. So resiliency in the fact that we don't even need this service could be failing over and you'll still be fine. Your primary node won't even know that it's happened. Then what happens is upon running checkpoints, essentially the log service will push that transaction down into the actual data file that lives on the remote storage. And then that's where the snapshots take place, and that's kind of how the flow of a write operation looks like. If we look at reads, so again, the big thing that you've got to understand about Hyperscale is that the performance will be somewhere between general purpose and business critical. Because today, a business critical deployment is 100% based on locally attached SSDs. A general purpose deployment is based 100% on remote premium storage. So because Hyperscale has a tiering of both of these, your performance is somewhere between and in some cases above. It all depends on your data access patterns, right? So if you have a workload that is very reliable, it kind of runs sequentially, and you access all the data that you've inserted recently a lot, there's a high likelihood all of that data will live in that really fast RBPX layer on the compute nodes, in which case your performance will be much closer, if not better, than business critical in some examples. So for a read, what happens is a user or an application will issue a read request for pages to the primary or the secondary in this case. So the secondary can also take read requests. There's two kind of outcomes that you... this is my old deck. This is the same one we went over. Do you know where the new deck is? Let's have a look. Sorry, this is the old deck. Let's have a look. Anyway, so I'll go to this one. It should be easy enough. All right, so when you have a read request that comes in, essentially what would happen is you have one of two criteria that's met. Right? The read request will come in, and the page that you require is either living on the RBPX of the compute node, in which case you have what is a cache hit. So you are accessing that data from the local SSD, and that is at sub-millisecond data latencies. The second outcome that could happen is you could have a cache miss, in which case that data is not in the local RBPX layer, and you have to go to the page server to go fetch that data. In which case you're coming down to the page server, which is 2 milliseconds latency down into that layer. So you can see very easily, right, like the more data you can fit into that local RBPX layer, the better your performance will be. So if you have this sort of a data pattern whereby you have a large data set, but you're really using a small subset of it at any given time, it is an ideal architecture for those type of workloads. And because of the high throughput, we can get into the log because of the way that the log landing zone works. For highly transactional workloads where you're doing big ET, or you're doing either big batch processing or like highly transactional workloads, you're also going to get very good performance in those scenarios. And let's just jump past all of these. I don't know why my slides are not updated here. It restores as well. But essentially, what would happen in a restore example is for the restores, we take snapshots at random time intervals for all the page servers. When you issue a restore operation to a specific point in time, we take the latest snapshots of each page server. We then take the last LSN up to the point in time that you want to restore from the long-term log storage, and then using a metadata operation, we would go and move those over into new storage accounts. We bring the page servers on, populate the page servers from the remote storage accounts, populate the local RBPX from those page servers, and then that way you would have an entire instance up and running within sort of less than 15 minutes, whether that was 10 terabytes or 100 terabytes. We can do that operation at exactly the same time, irrespective of size of data. The last thing that I'm going to cover, just to kind of set a bit more context so that everyone kind of understands where all of this sits. As I mentioned, today, general purpose is solely based on Azure Remote Storage, right? It's about 2 milliseconds for all data access operations. Business critical being our sort of top tier deployments, that is all only utilizing the local SSDs that sit within the actual primary node. And then Hyperscale is kind of a blend of these two things where you have the highly performant local SSD layer that is acting as a buffer or as a cache extension, and you have the page servers that are running on premium remote SSDs that also have full covering RBPXs on them. And then finally, you have the offload into the standard storage where all of your backups and those operations are taking place. And then I'm going to hand over to Xiaoxin, and he's going to tell you why all of this matters for developers.
Thank you, Alan. I got about 20 minutes. I'm surprised I got so much time. Usually, if you're the last one of the 3 speakers on the stage, you got like 5 minutes. It's like when you're a developer, you are owning the last component which you'll be integrating into your system. And so because I got a lot of time, before I get started, I'd like to ask a few questions. And we get some swags if you volunteer to answer those questions. So does any of you already have some idea in your mind that how Hyperscale can benefit you during your development lifecycle or for your project? Can you raise your hand if you have anything in your mind? That gentleman with hat. Great. So the answer is rescale and IO throughput. Anyone else? Sure. Yeah, again, it's about disk I/O. And let me ask another question. How many of you here are developers? Most of you. How many of you here are DBAs? Few of you. I heard DBAs don't come to this conference, but welcome. I mean, I/O, the disk I/O, memory I/O, and also the RAID skill, those are all good points. And also, a few folks on the back, if you fall asleep, please wake up, because the next 20 minutes is very important to you. I'm going to talk about those stuff your boss is going to ask you. When he asks you what's your takeaway, what you learn from the session, those will be the answers. So the question? Great. Yeah, that's a great point. So you can leverage this snapshot backup and the fast point-in-time restore to get a copy of your large production database into your test system. So here, I'm going to show you how Azure Database Hyperscale can benefit you through the whole development lifecycle. I'm using CI/CD as an example, but it also applies to other development models, like if you use waterfall, use Agile, it doesn't matter. It's the same concept and the same philosophy. So the Hyperscale Database, as a new PaaS offering we're having in Azure, it's going to benefit you during the whole lifecycle, starting from evaluation, planning, and then coding, testing, and integration, deployment, and end with operation and also monitoring. So let's start from evaluation and planning. I used to be a developer for about 10 years before I became a PM who's standing here and talking to you. And I remember my first project that was in a lab when I'm getting my master's degree. It was like 2005, 2006 timeframe. And my professor said, hey, let's build a database for all the test data set for the whole lab. I said, OK, let's do it. And I decided to do it on top of SQL Server 2000. And the first thing I did is I go talk to the admin and say, hey, give me a machine. And then I put together a machine and connect the monitors, and then install Windows, and then install SQL Server. That took me a week. And then I get some data in there and write some code and have the application running. And the second week, my boss is like, oh, you only have like 30 gigabytes of disk. That's 2005. We need more disk. We need more data. So I go to the admin and get more disk and connect to the machine. And after a few months, everything runs well. And then my boss is like, oh, there's SQL Server 2005. Let's use SQL Server 2005 instead of SQL Server 2000. Is any of you have ever tried to upgrade a SQL Server 2000 to SQL Server 2005? 1, 2, 3, 4, 5. That's almost impossible. So with Hyperscale, first of all, during your evaluation and planning stage, you don't have any upfront cost. You don't need to go to your admin. You don't need to go to your finance people to say, hey, give me the money to buy those machines. So you don't have to do hardware installation. You don't have to do software installation. And you can save tons of money and also tons of time, which is even more valuable than money. And Hyperscale, as an Azure database offering, it provides a very clear, defined cost model. There's no hidden cost. Everything is listed there, and you can very easily to calculate how much it's going to cost for your dev test database, how much it's going to cost for your production database. And we also provide a very flexible pricing model for different types of workload. So for burstable workload, and we just announced Azure SQL Database serverless yesterday in Scott Guthrie's keynote. And that will help you to handle those unpredictable burstable workload. And for your standard workload, you can just use our default, which is pay-as-you-go model. And if you want to have a long-term commitment, for example, you know you're going to run your application in Azure for the next 1 year or 3 years, you can also choose to use our reserved instance, which can help you to get up to 70-something% discount. And if you're just a developer and you don't want to pay for a production cost before you know that you can run your application in Azure, you can also leverage our MSDN subscription and also our dev test subscription, which is the EA version of MSDN subscription. Let's say your company signed a contract with Microsoft. You can create a dev task subscription and use Hyperscale Database without paying for the SQL license. And in the end, we also have this Azure Hybrid Benefit Program, which allows you to bring your on-premise SQL Server license into Azure and get up to 43% discount. So once everything is planned, and now you will start to write your code and test your database. So first of all, you should forget anything Elaine just talked about in the past 20 minutes. Hyperscale is just SQL. The same interface, the same T-SQL syntax, you can use all the tools, all the drivers, all the frameworks you're using today. And you can use all the PowerShell, CRIs, and REST APIs you're using today to manage and create your Azure SQL database. Nothing is changed. And with Hyperscale, we also provide you an option to create a database with a minimum cost. So first of all, you can create a database with only 2 vCores and a single replica, where we still provide high availability, but just lower SLA. In most of the cases, for your dev test database, you don't need to run this database for with 4.9 or 5.9 SLA. If it's down for 1 minute or 2 minutes, it's not a big deal. So Hyperscale gives you this flexibility to minimize your dev test cost and also pay your database storage only by usage. You don't have to reserve and pay upfront cost for the data storage. And as that gentleman just mentioned, that Hyperscale gives you an opportunity to very easily set up a test environment and copy your production database to a test environment by using point-in-time restore. So Elaine and Kevin just mentioned that the point-in-time restore operation will be a constant time operation regardless of the database size, which means if you have a 10 terabyte, 20 terabyte, 50 terabyte database running in production, and you're trying to create a dev test environment, that will not take weeks anymore. And also, in some cases, for example, this friend just mentioned he's from healthcare. When you're in healthcare and you're in financial companies or other companies who's handling sensitive data, the customer data like SSN and other sensitive data, you don't want to give all those data to your developers because you cannot trust all of them. It could leak your customers' data. It could have some compliance or security issues. So Hyperscale, as a Azure SQL Database offering, it can help you to prepare your text database and protect your sensitive data by leveraging our integrated Azure Active Directory authentication and also using one of the SQL Server feature called dynamic data masking. So you can define which user can see which data in which format. For example, you can define to say, hey, your developers and testers can only see your customer's SSN with the last 4 digits. Or you can say, I'm going to mask the telephone numbers. It will be still will be distinguished numbers, but it will be different numbers. You cannot just get the number and call my customers. And also for Hyperscale Database, you can very easily and very fast scale up and scale down your database. So you can work on you can write in your code and test your database with a very minimum configuration, like 2 vCore or 4 vCores. And when you're trying to do a scale testing or load testing, you can easily bump up your database and create a 40 vCore or 80 vCore database. Or you can choose to use the read scale out by adding multiple replicas. So in that case, in that way, you can easily change your test environment to support your stress and load testing. And again, all those scale up and scale down operation will be a constant time operation regardless of database size. So next, I'm going to show you a quick demo about how to copy a 50 terabyte database from your production environment to your test environment by using point-in-time restore. So this is a pre-recorded video. So what you need to do is just go to Azure portal and then find your database and click on the restore button. And then you can give the new database a new name. And then you can choose the point in time and click OK. And this will be running behind the scene. Because this is still going to take about 7-8 minutes, I'm not going to show you the whole process. But you can see a timer on the up right corner. The timer will tell you how long this operation is going to take. So by leveraging this, you can copy your production database into a testing environment very efficiently. And also, when you don't need it, you can just drop your test database, because we also support you to restore a deleted database from the backups. And also, you can use this to reset your testing environment. So let's say in the morning, you come to the office, and you have a test database, and you're running some tests. And tomorrow, you want to repeat the test again. So you can just do a point-in-time restore and restore database to the time before before you were doing the test. That will reset all your data, and then you can repeat your test again and again and again without paying extra cost. So now you see we shift to near the end of this test. It's still running. It's about 7 minutes. Now you can already see the database in the database list. But we're still doing some work to finish up this restore process and provide you the external access to the database. It's about to be done in a few seconds. Finger crossed. If I'm right, it's 3, 2, 1. Wait a minute. Again, let me try it again. 3, 2, 1. OK, I'm wrong about the time. But anyway, it will be finished very soon. So the point is, it is very easy and a very cost-efficient function. Now it is finished. So you can see the operation is finished, and you have another copy of your 50 terabyte production database in your testing environment. It is a very financially efficient and also time-efficient function for you to replicate your production data and create a testing environment. So the next stage of your development cycle will be integration and deployment. So you write your code, you test your code and test your database. Now you want to integrate it into your production environment. This will be a very risky and nobody want to do it operation, because anything can happen. You could cause a regression, your database could run down, you may have like a schema change which is not compatible with your application. But Hyperscale provides you a worry-free integration. So previously, without Hyperscale, before you're doing this type of deployment, you may need to make a copy of your database. So in case something happened, you can just fast roll back to your original database. But if you're doing like an online upgrade, you still lost some data during this upgrade. So you may need to talk to your customer, oh, you need to do this again. Or you need to like restore all the backups. If you have a 50 terabyte database, restoring from backup, good luck. That's going to take days, if it's not weeks. But with Hyperscale, you can fast roll back your production environment by using point-in-time restore to the time before this integration happened. If something happened, you can recover your production environment in less than 10 minutes. And also, the Hyperscale database is integrated with Visual Studio. So you can deploy your database together with your application code using DACPack and using SQL package. And we also have built-in high availability for Hyperscale. So you can focus on your application instead of spending time to configure the high availability of your database. And at the same time, we also have different security features to help you to protect your data or your customers' data in your production environment, including TDE, which is a transparent data encryption. It is default turned on in all the Azure SQL databases, which makes sure your data is always encrypted at rest. So which means if someone just get into your Azure data center and physically took the disk, they still cannot get your data. And also we have other features like firewall rules. You can define who can access your database from which IP address they can access your database. And the last, you deploy all the applications to the production environment. You have your database running, everyone's happy. But you still need to do those operations and also monitoring works to make sure that everything is running OK every day. So first of all, Hyperscale database and all Azure databases provide auto-patching and auto-upgrade. I don't have to upgrade a SQL Server 2000 to SQL Server 2005 again, or upgrade to SQL Server 2017 to SQL Server 2019. So you'll be always running the latest and the greatest version of SQL Server. And one of the issues this auto-patching is bringing up is that our vendors or our partners, it is hard for them to certify Azure SQL Database because we keep rolling out these new versions and new features. So to solve those issues, we introduced this new database compatibility level-based certification. So you can certify your tools, your services, which is running on Azure SQL Databases based on database compatibility level instead of the database version. And when you're ready to upgrade your tools, upgrade your service, and you can bump up this database compatibility level and use our new features introduced in Azure SQL Database. And auto-tuning is one of my favorite features if I'm still a developer. So this feature helps me, which I don't know much about SQL Server, to tune my database performance automatically. So it will monitor your database activities and all the queries you're running, and give you advice to say, hey, you need to create an index on this table, or you need to drop an index from this table to get better performance for most of your queries. And you can also turn on this auto-tuning, which means it will just do it for you. You don't have to worry about the database performance anymore, and you will get optimized performance for all your databases automatically. And we also have these intelligent performance features to help you to easily monitor thousands of SQL Server databases running in Azure DB. You can pull all the diagnostic logs and the performance logs into our OMS, the operation management suite, and operating and monitoring and your database from there, and then create an alert. For example, if I see my database CPU usage is up to 90% in the past hour, you should send me a text message or send me an email. So I will know that I will come online and upgrade my database. And you can also use this mechanism to create automated operation solution to do this automatically. And we also have a bunch of intelligent security features to help us to protect your data or protect your customers' data. So one of the feature we call advanced threat detection. It is a machine learning-based security feature which can monitor all the activities happening in your database and protect your database and alert on abnormal activities. So for example, if all your customer is based in US and suddenly there's someone who's trying to connect to your database from Japan, then that could be an attack or something wrong happening. So in that case, if you configure threat detection, we're going to send you an alert and say, hey, there's an IP address which is in Japan, is trying to connect to your database, and this is 1, 2, 3 steps you need to do to mitigate this issue right now. And also, we're going to give you the recommendation to say, how can you prevent this from happening next time? So for example, in this case, we're going to say you need to configure your firewall rules to block those those IPs which doesn't belong to your customer or doesn't belong to your organization. So to summarize what we talk about today, so this will be our takeaway and what Hyperscale brings to you. It is a mission-critical, high-performance, high-scalability, high-reliability database running in Azure. It's a PaaS service. It provides you all the PaaS features, including built-in HA, automated backup, all the security and performance features. And it provides a seamless, tunable performance and scalability. You can have a 2 vCore database, which is a 100 terabyte. You can, at the same time, you can also have a 5 gigabyte database and have 80 vCores running on top of that. And you can grow your database in cloud, and technically it's unlimited. And you have this constant time backup and point-in-time restore, which help you to create or reset your test environment from your production data. And we also have all the future innovation built in. We just started this work like a few years ago, and this will be the first version of Azure SQL Database Hyperscale. We have a whole team working on this and providing more. We are going to build more features and provide to you guys. If you want to learn more about Hyperscale, you should go to the Azure portal now and create a Hyperscale database and scale one of your existing Azure SQL database to Hyperscale. Before doing that, please note that this is a one-way operation. Again, this is a one-way operation. There's no way to go back until we provide this feature. I will guarantee you we will do this, but not today. And also you can go to the documentation site, and also you can learn the price of Hyperscale from our pricing page. Let me switch to this one. So please go to the mybuild.microsoft.com to provide the feedback. Your feedback is very, very valuable to us. And again, thank you for coming to Build Conference, and thank you for coming to today's session. We don't have time for Q&A, but me, Ellen, and Kevin will be outside this room. So if you have any question, feel free to stop by. And we'll also be at the Hyperscale booth at the expo area. So you can stop by today or tomorrow if you have any further questions. Thank you very much for coming.